Good afternoon, and always nice to see you here. Today we have an exciting speaker, and I can't wait to hear his story, long journey here at Gordon. Of course, some of you know Joe has been here for 38 years.
38.
Probably going to 39, so that night. And to help us, of course, introduce Joe is one of the associates who have been working with Joe for a very long time. And if we squeeze all the years Joe has worked into 12 months, we can almost say that she's been here now 10 months. So that tells you how long she's been here. So Lina Ilder is going to introduce or make some remarks about Joe, and after that we'll be on our way running. So please help me welcome Lina Ilder.
Hello, everybody. I started working in Joel's group over 30 years ago, and I can honestly say that there's never been a dull moment. Joel finds the research he's involved with exciting, interesting, and always a fascinating puzzle that he's determined to solve. Whenever someone in the groups describes something unusual that we see in our data, we know that he won't rest until he thinks of a reasonable set of conditions that caused it and then find a solution for the issue of concern. I can't count the number of times that Joel has walked into the office in the morning and said that he woke up in the middle of the night and had an epiphany. So this must mean that Joel truly has a dream job. Joel, incredibly, can juggle many ideas at one time. I remember many years ago when there were 5 of us in Joel's group who all shared a large office. Joel would walk into the room and go from desk to desk to find out what new results we had to share with him. He would get excited over the results discovered, ponder the next step in the research, and then move around the office to the next person, who was usually working on a completely different project. By the time he took those first few steps to that next desk, you could already see him switching gears in his mind and was peppering them with questions and ideas. It was an incredible sight to watch. After years of working with Joel, I am amazed at his sorting and filing system. What looks like just a pile of papers on his desk is a unique and astonishing system. Joel could walk into his office and within seconds find anything he's looking for. And the only time I've ever seen this system fail was many years ago when we were all moving offices. Joel happened to be away at a conference on moving day, so Joyce carefully unpacked and set up his office for him, shelf for shelf, drawer for drawer. However, the new office was an identical mirror image of the old one, and it took Joel weeks to find anything. Something you might not know about Joel is he's a big sports fan. He watches baseball and football games and knows an incredible amount of stats for college basketball and football. He's always willing to describe the latest and greatest plays of recent games and how that changes the standings. It's almost with the same level of enthusiasm that he follows the polls and political candidates. And if you've ever been to Joel's office, you know that he loves classical music. You might not know that he's also a big fan of music from the 1960s and is probably the only person that can understand what Bob Dylan is saying. But if you really want to see Joel's face light up, ask him about his grandchildren. To him, his family is everything, and they are indeed his pride and joy. Please welcome Joel Suskin.
Okay, the title of the talk, you see, is Journey from Chemistry to Who Would Have Thought It? Meteorology. I'll be talking about how I got from there to here. So as a child growing up in Brooklyn, New York, I used to love to mix things together to see what happened. I had a 9-year-old brother. Here's a picture of me and my brother. I think I was about 6 months old here. I found this. It's a great picture. And he had a chemistry set when he was young, and to make hydrogen sulfide in the kitchen, and also to copper plate the silverware. I actually spoke to him last week. I told him about this talk. He said, those were the only 2 things I ever did with my chemistry set. But my mother was not amused, so she didn't let me have a chemistry set. But I had a friend living down the block who had he had a biology set. It had some chemicals in it. He had ferrous sulfate, light blue crystals. My mother had some ammonia. I'd mix them together and see the colors change. I'd like to mix things where fumes would come out. So this was my first step in a long journey. Okay, I went to high school in New York, in Stuyvesant High School. It's in Manhattan, and take a subway ride. It was a special school. You had to take an exam to get in. It was a special science and engineering high school, and I especially loved chemistry and mathematics over there. I had this wonderful teacher, Mr. Atkin, for honors geometry and honors intermediate algebra. Now, in New York, the way they graded you was from 0 to 100. 100 was a perfect grade. With him, got 100 on everything. You couldn't get more than a 95 for your grade unless you solved the prize problems. And I solved every single prize problem that we had except for one. In fact, I should have known this was going to be a tough one. We usually had a day to do a prize problem. They gave us a week to do this, and I spent all week and couldn't figure it out. There was one genius student who got it, so I'm just going to show you the problem right now. And expecting everyone to, of course, get it. So the problem is this working? Yes. Problem is simple. Here's a piece of paper. It's on its side. We have this huge triangle somewhere here. And they go, it doesn't meet on the paper. And the problem was to construct the angle bisector of these lines where you don't know where they meet. And you can't do anything. Anything you had to do was on the paper. You couldn't do anything off the paper. So I'll give you a hint now. And that's something, we knew. It was a theorem that said the angle bisectors of a triangle, all of them meet at a single point. So that should be enough. We didn't even get that clue. That should be enough to help you solve this problem. But I'll just let you know, my last view graph, I'll give you another hint. OK, so let's go on. So I went to college in Columbia, in Manhattan. I took the subway a little further. And I started majoring in both math and chemistry. Those are things that I loved. As a sophomore, I took organic chemistry, and I hated it. For one thing, I'm a real klutz in the laboratory. My wife, Leslie, who's here, can certainly attest to that for anything around the house. So actually, I got a B in that class. It was the only class I got a B in. But there were about 100 students in the lecture class of organic chemistry. We had this big lecture room. And we only had 10 chemistry majors. Everyone else was pre-med. But the best thing I remember about that class was every Monday, it was 10 o'clock, a bunch of us chemistry majors would sit together, weren't paying any attention to what the teacher spoke about, and we'd talk about the wonderful thing that happened in Sunday's Bullwinkle show. So that's my fondest memory of organic chemistry. In my junior year, I took a class in physical chemistry. I loved it. We were learning a little bit about quantum mechanics. And I also took a class, turned out to be a mistake, maybe not a mistake. I took a class, an advanced mathematics class. In fact, it was a graduate class, geometric topology. It was extremely abstract. It wasn't helped by the fact that my professor, world-famous genius, was from Japan, and I couldn't understand a word he was saying. Anyway, I remember I didn't know what was going on. We had a quarterfinal. And I think I got 10 out of 100, which was a good score. Many people got 0. But I decided to drop the class and to continue with chemistry. There were a couple of superstars that ran up to the board and were showing the professor how to do it. So I figured I'd stick with chemistry and forget about mathematics. My goal then, as it was for a long time, I wanted to go into academia. I wanted to be a professor of chemistry. So, of course, I was going to graduate school, so I was going to go to get my PhD somewhere. I applied to a number of places. I narrowed it down to staying at Columbia and going to Berkeley, UC Berkeley in California. And my professor said, Joel, why don't you go to Berkeley? It's good to see a new, a different chemistry department, what different people are doing. And also, you'll find it interesting over there. Well, sure enough. I got to Berkeley in 1964. I was there from 64 to 68. And for those who know, it was a pretty exciting place at that time. We had a lot of protests about the Vietnam War. Leslie and I took part in many of these. By the way, it was exciting another way. You mentioned Bob Dylan. You know, Bob Dylan would come to our campus and give. Joan Baez was there. You know, it was a lot going on culturally and all kind of things like that. So, and anyway, I got a huge culture shock coming from New York when I went to California. I flew from New York to San Francisco, and they had a special deal at the time. If you fly cross country, they give you a free helicopter ride to the Berkeley heliport. You go across Oakland Bay. So I took the helicopter ride, and then I took a taxi toward UC Berkeley. It was this big street, University Boulevard. It's a 6-lane street, and my taxi is going in the leftmost lane heading that way, and the pedestrian puts a foot in the crosswalk on the other side of the street, and the taxi driver stopped. It blew my mind. Coming from New York, you know, if you're in a taxi and someone walks, no one would dare walk in front of you, but if they did, they'd hit you. So, I mean, I couldn't believe this. So with all this stuff going on, I did have a big culture shock going to California. And just to follow up on that, my friend Dennis Travis, who was one of the super geniuses in math at Columbia, he came to visit me. We had this big street, downtown Berkeley, again, a 6-lane road. He put his foot into it, and it, not in the crosswalk, and he immediately got a jaywalking ticket. So, you know, so much for liberal Berkeley. Well, I found a professor to do research with, Professor William Gwynn, and his research group performed laboratory gas phase microwave spectroscopy with an emphasis on making advances in the quantum mechanical theory of vibration, rotation, coupling, and its effect on absorption line positions and intensities. And I was particularly interested, we looked at motions of one part of a molecule with another. I was particularly interested in the effects of what's called internal rotation. Here, I'll take a look at this. Internal rotation of a methyl group. This is a CH3 group with respect to something else. This is the molecule I worked on, orthofluorotoluene. Toluene is a benzene ring and a methyl group here, and it rotates, it actually vibrates. Interesting things happen. And you have a certain symmetry here, but if you stick a little fluorine on there, it changes the symmetry a little bit. And I was particularly interested in breakdowns in symmetry, so I wrote a thesis on this molecule. As I've already said, and I was a klutz in the lab, but my professor, he insisted that, this chemistry department, he insisted that all his students take their spectra and analyze. And my interest was the quantum mechanics. He said, you're tying one hand behind your back if you're only doing the theory. Okay, so let me say something about quantum mechanics. There were 2 different approaches to quantum mechanics that were published in 1925. One was by Schrödinger and Heisenberg. They were totally different. Schrödinger's approach found solutions to differential equations, and Heisenberg's approach used no explicit math, but involved the use of matrix representations of different geophysical parameters, such as the position vector x, that's where something is, and its momentum p. Now, these 2 different approaches were later shown to be scientifically equivalent. They came from totally different places, but they were absolutely equivalent one to the other. And fortunately for me, everything our group did was in matrix mechanics. I'm a whiz at matrix mechanics. But to this day, I couldn't solve a differential equation if my life depended on it. So I would have been in a different field and probably not here, given my track, if we did differential equations. Well, let me say a few words about Professor Gwynn. He was an incredible genius. He had an enormous intuition that I admired and learned a lot from. Now, you can't teach somebody to have intuition, but you can't teach somebody how to use intuition. And I mean, I saw how he thought, and all the research I do is based on use of intuition. In quantum mechanics, it was especially the significance of off-diagonal matrix elements. Now, he never really spoke to his graduate students until he could learn something from you toward the end. So we had a wonderful research group. Usually we were there for 4 years, so I was in my first year with 2 other graduate students, and we had second year, third year, fourth year, and I interacted with them and learned a lot from them. Professor Gwynn, we were having a great time. I was partying, beer and pizza every night. And after 3.5 years, he comes and says, Joel and the others, be done in 4 years. So I finally had to do something. But also while I was there, he arranged a postdoc for me with his colleague, Professor John Overend, in the chemistry department at the University of Minnesota. So, I had to get something done. I finished my thesis. And this is a profound lesson I learned. I finished my thesis, and I spent 2 hours talking to him, showing him this, showing him that, showing him this. He says, Joel, do you mean to say this? I said, how can you say that? I've been talking to you for 2 hours. He said, you weren't talking to the reader for 2 hours, and that's a very profound lesson. If someone can misinterpret something, they probably will. So I had my first postdoc in the University of Minnesota. I was there for 2 years, 69 to 70, with John Overend. And this was a big change and a little change. He was doing high spectral resolution infrared gas phase molecular spectroscopy. Infrared spectroscopy, it's a higher frequency, so investigates vibration and rotation transitions between molecular quantum states. Microwave is just rotation. It's a lower frequency. And I was still enamored with my internal rotation of methyl groups, so I went full out. I studied ethane, CH3, CH3, 2 methyl groups. And I derived my own theoretical approach to analyze this data, which of course I was using matrix mechanics. Nobody else, the professor, nobody else did anything like that. But I showed them how to think that way. And it's an extremely complex problem with different states, coupling different states in this and in this. But I looked and said, hey, look, this is what's important. This off-diagonal matrix elements are important. Those are not. People would write pages and pages and pages of equations. I do a simple matrix calculation and get a better result. So, by the way, this type of research was called chemical physics, and by everybody else in the chemistry department was considered to be physics. Now, as I said, my career goal was to be a professor of chemistry somewhere, physical chemistry, but there weren't any positions available at the time. So it's not what I wanted, but this led to my second postdoc position. And my second postdoc was at Florida State in Tallahassee. It was with Professor Robert Hunt in the physics department. Now, I went there. I didn't want another postdoc, but he said he'd heard about my work. Joel, it's very important. We want you. And there was a promise that in a year or two they'd have a professorship in Florida State, so I went there. And again, we were doing high spectral resolution IR gas phase molecular spectroscopy. But I learned 3 huge differences between physics and chemistry. One is in chemistry, what we were doing was considered physics. In physics, at Florida State, everything we were doing was considered chemistry. So that's one big difference. Another difference is in physics, you are either a theorist or an experimentalist. They could tell that I was really a theorist, not an experimentalist, so they wisely didn't let me near the lab. So I was analyzing data that other people were taking. And another difference is that in chemistry, you'll notice I had a couple of carbons, ethane, 2 carbons. In physics, if it's more than 1 carbon, that's chemistry. So I had to work on methane, CH4, and CO2, doing the theory of absorption spectra of those gases taken by others. I also got involved with a chemistry department at Florida State. There was a nice professor over there doing very interesting research that I'll talk about in a minute, molecular spectroscopy. And I was told a faculty position might become available in chemistry. So I said, let me give it a try. So I did some work with the chemistry professor and his group. It's ultraviolet, so it's higher frequency yet. It's electronic transitions. And that group was studying ethylene, C2H2. Note, it's 2 carbons. They could do that in the chemistry department. So now this group, ethylene in the ground state, electronic state is planar. It's in a plane. The first excited state, it's twisted like this. And they couldn't figure out why. I mean, they could tell from the spectra. So I looked at it. I said, come on, of course this is the case. I ran up to the blackboard. I wrote some off-diagonal matrix elements and said, sure, look. They were shocked. turned out here that, I was doing work in both chemistry and physics department. They both loved what I was doing, really important, but times were tough. They didn't get the funding to hire either a professor in chemistry or physics. So, meanwhile, I was looking at faculty positions all over the place and not finding anything. So I was, this was a bit of a crisis at the time. I had a 4-year-old child, no job prospects. I didn't know what I was going to do. Spoiler alert, it worked out for me. Here I am. And, I'll tell you now how I got from there to here. And there were some interesting things that happened. But also, let me just say, I have 3 sons. I've told them all. And I'm telling others, sometimes you don't know how things are going to work out. But they do. Things work out for the best. OK, so now, a very important thing happened. I mean, I told you I didn't have a job, nothing. But racquetball was an enormous, wonderful thing. My professor, Hunt, played racquetball with John Gilly. Some of you may recognize the name. He was a professor in the meteorology department at Florida State. And he had developed a satellite-borne limb-scanning broadband IR radiometer to measure trace constituents. And John was leaving Florida State to go to NCAR. And he knew, I mean, Bob Hunt was telling him about what I'm doing. Joel, we need somebody like you. So he said, I think I can get you a position at NCAR, regular position. Okay, it's not professor, but sounds interestingly enough. So I went with him at the time to the first radiation symposium in Fort Collins. This was in 1972. And then I gave a seminar at NCAR, and then John said, Joel, I'm sorry, I didn't get the funding that I have. I can support you for 2 months to do some calculations for the spectra of nitrogen dioxide. I want to measure nitrogen dioxide. It's an interesting molecule. Do the calculations, and I could perform the work anywhere I wanted. Well, interestingly enough, I met this fellow Steve Schneider. Some of you may have heard of him. He made quite a name for himself in climate. I met him at NCAR, and he had just left the Goddard Institute for Space Studies, GISS, to go to NCAR. I said, why don't I go to GISS? I mean, I live in New York. I have family over there. It's as good a place as any to do something for 2 months. What's going to happen after that, God knows. So he told me to go see Joe Hogan at GISS. Well, so I went to Joe Hogan's office at GISS to tell him I needed a desk and some computer time at GISS to do molecular spectroscopic calculations for John Gilly. And Joe Hogan said, Joel, John Gilly told Joe Hogan about me, and we need somebody like you. I'd looked all over the place. I walk in off the street, and there we are. So it turned out that I received another postdoc position at GISS in New York, National Research Council postdoc position, postdoc number 3, to work with Dick Stewart, who some of you may know from here. He's recently retired a few years ago. I'll get to that. And Dick was studying sources of pollution over land. And of course, I was hired to do quantum mechanical calculations again. After 1 year there, Milt Halem, some of you might know the name Milt Halem, at GISS told me, Joel, I need you to support my research, his research, to compute atmospheric transmittance functions for the VTPR broadband sounder, which flew on NOAA 5. Transmittance functions are calculations to show how the atmosphere absorbs in these spectral bands as a function of temperature, water vapor, what have you. Because if you can analyze the data, you have to know the physics. So at that point, I became a contractor to support Milt Halem's research. And you'll note that there was no meteorology yet. I'm still doing quantum mechanics here. Well, still no meteorology, but I began to move in that direction. I got into temperature profile retrievals. I was computing transmittance functions for these instruments. Now that I measure this, determining temperature. And I had a wonderful colleague, Mushaheen. He worked with Milt Halem. He was one of the rare collaborations of JPL and Goddard. And then he and I became very strong collaborators. And he said, Joel, we're really unusual pair. Usually they're competing for money or something like this. Anyway, unfortunately, Moose passed away suddenly 2 years ago. That was a big loss to everybody. But he was doing theory of how to analyze these satellite sound or broadband radiance measurements, infrared under partial cloud cover. And following Moose's theory, I developed and implemented an algorithm to retrieve temperature profiles from VTPR, and we began to analyze the VTPR data. It's just a 15 micron band, it's broadband channels. But Moose's theory also showed that, hey, you could do even better under partial cloud cover if you have channels in both the 15 micron band and the 4 micron band, which is another band at a higher frequency. Now, Nimbus 6 was launched in 1975 carrying the HERS instrument, which had both 15 and 4.3 micron channels. And I was getting into temperature retrievals here. I developed an improved algorithm based on Moose's work where we used the 15 and 4 micron channels together, and I showed that we could do much better and I showed that we could do much better retrievals than VTPR under cloudy conditions having both. I'm going to talk about the Green Tree restaurant, and it's a wonderful Hungarian restaurant a few blocks from GIS. One day I had lunch there with Luke Kaplan. Yes, Luke Kaplan, a tremendous pioneer of satellite sounding research. He had been from the University of Chicago, but then he came back to the government, so he was working with us for a while. I had lunch with him, with Moose Shaheen and Milt, and Luke took a napkin and scribbled a couple of equations on it. And these equations showed, hey, if you have high spectral resolution and look in between the absorption lines, you could get much more information about what's happening in the atmosphere. You get sharper weighting functions. The response to the atmosphere is much narrower. And also, if you also have high resolution measurements at the high end of the 4 micron band between 2378 and 2390, this would really do wonders for you. And this napkin led to the design of the AIRS instrument flying on ELS Aqua. And AIRS can be thought of as the Green Tree restaurant sounder. It was the inspiration for this. Okay, in 1977, Milt Halem moved his group to Goddard here. And he became head at that time of the Goddard Modeling and Simulation Facility. It wasn't a branch or anything because he was a civil servant and I was his first civil servant, so there were just two of us. We had a bunch of contractors and what have you. And I was put in charge of analyzing satellite sounder observations. That was my responsibility. Shortly afterwards, he hired Bob Atlas, who some of you might know, and he was in charge of data assimilation research, or Eugenia Kalnay in charge of global weather research, and Jagdish Shukla in charge of climate research. And what I was doing then was doing temperature retrievals from first from VTPR and then from HERS, and passing them on for Bob Atlas for his use in data assimilation experiments. In 1982, GMSF became Goddard Modeling and Simulation Branch. That's after we hired some more civil servants, so we were a branch. And we were located in the ground floor of Building 22, and I spent most of my career over there. It's only a few years since I'm here. 3 doors down the hall from me was a young biologist, Piers Sellers. Piers and I became very friendly, and I really liked his sense of humor. Well, now I'm going to talk about the TOVS Pathfinder Path A data set. TOVS, the TIROS Operational Vertical Sounder, was first launched in TIROS-N in 1978 and was comprised of a HERS-2 instrument, which is a somewhat advanced version of HERS, and also the microwave sounding unit, MSU, and it later flew on NOAA 6-12 and also on NOAA 14. NOAA 13 failed at launch. NOAA 13 had 2 things going against it. One was the unfortunate number of 13. 2 was that was the only launch I attended. So I went there and the launch failed. But nevertheless, we developed this Pathfinder Path A retrieval algorithm that contained further improvements in retrieval methodology, and in particular, the use of microwave observations. We never had microwave before, and they're a very useful part of the suite. And we analyzed TOVS data using this methodology for the period 1979 to 2002. when TOVs on NOAA 14 began to degrade. And we had this big data set, and it included surface skin temperature, temperature and water vapor profiles, total ozone, cloud heights, fractional cloud cover, and outgoing long-wave radiation, OLR, which is a product that's computed from everything else. And it contains daily, 5-day, monthly mean values of all of these products on a 1 degree by 1 degree lat-long grid. So I began to learn a little meteorology by looking at the products. I mean, I never took a class, I never did anything, but it was just obvious looking at the things that we had that I could see what's going on. I'm relatively self-taught. And some of the really important things that depicted were the short-term climate trends over this period, interannual variability, and especially the effect of El Nino on anomalies. So I began to get into meteorology in spite of myself here somehow. So now I want to change tack a little, and I'll talk about holiday parties. Following a tradition from GISS, Milt Halem always had a holiday party around New Year's Day. There was always plenty of good food, good beverages of all types, if you get my gist here. Real good camaraderie between everyone. And during the party, Milt always spoke of all the great things that our branch did during the past year. He gave out awards, and somebody always took pictures of the event. This tradition continues to this day. This Sunday, I had my holiday party in my house, and a number of us were here. It was supposed to be the second week in January, but a little snow got in the way, so we just had it last week. But I'm going to show some pictures now of some of these parties, and some of the people at these parties made quite a name for themselves, especially a young child. So here, let me look at this. This is a party. Can you see this? This is a party from 1979. Here's Milt Halem, our branch head. Here's Dave Atlas, who was our division chief. He was Steve Platnick now. Wayman Baker was someone, one of our civil servants who's at NOAA right now. This is a picture, Eugenia Calnay, Lou Uccellini. Lou was not in our branch, but he was just down the hall, and we were very friendly with him, so we did a lot. They've made names for themselves here. Here's 1982. Milt is giving me an award of some sort. Here are two pictures from 1983. Michael Gill. He was a professor at UCLA, but he spent a lot of time with us he was a climate scientist collaborating. And here's Eugenia Calnay and Jagdish Shukla. And here's this little kid, Sergey Brin. He was the son of Zhenya Brin, who supported Bob Atlas in data assimilation work. He worked with Bob Rosenberg here. And I always thought he was a pretty bright kid. I thought he'd have future. So he made out okay. Here's some more pictures. Here's a picture from 1984. Here's Marvin Geller. He became the next division chief. Jagdish Shukla was at this picture. Yale Mintz, who was a professor at UCLA, who collaborated a lot with us on climate research. And here was Piers Sellers at that party. Piers was not part of his group, but down the hall, and we were friendly and this and that. Here's some more pictures. 1988, here's a picture of Chuck Cody, who was the deputy to Marvin at the time. He's still here. He's since retired from the government. Picture of myself and my charming wife, Leslie, who hasn't aged a bit. Here's one from 1990. Bob Atlas is here. Here's Bob Rosenberg. He hasn't changed a bit. And here are his two older daughters, Sarah and Bonnie. His youngest one, Melanie, wasn't born yet. And here's one from 1999. Here's Milt again. Myself, Bob Atlas, Wayman Baker, and Jeff Chen. He was the project manager of the contract that was supporting us at the time. Okay, well, there was some organizational changes that I address. Milt became the chief of the Space Science and Computing Division in 1984. And he asked me to join him and become a branch head over there. And I turned down the offer because I was having too much fun doing what I was doing. Let me give you this anecdote. He was very disappointed. He told me this right before Hanukkah. I said, I'm not going to do it. He said, Joel, I wish you a miserable Hanukkah. Anyway, at that point, Eugenia Kalnay became the branch head of GMSB. Eugenia left to join NOAA. Eugenia was followed by Ray Bates as branch head. He was from England, and then he went back to England. And in 1992, Franco Einaudi, our old division chief, who I have memories of, I'll leave out the word fond, dissolved GMSB, and he split it into two groups. One group, remember when I was telling you what we were doing satellite research, data assimilation, climate, this and this and this. So he made one group called the Satellite Data Utilization Office. I was the chief of that. It was an official government management position. Bob Atlas worked for me and others, and the Data Assimilation Office, DAO, which was the precursor to the Goddard Modeling and Analysis Office. In 1995, Franco dissolved my office, and I then became a senior scientist in the Laboratory for Atmospheres as the informal head, spiritual leader of the Sounder research team, in which I was and remain the only civil servant. I mean, it's called a team because there are no other civil servants in it, so there's no government. I'm not a manager. Now, I've had, some of you may know from now, I've had some mission support contract responsibilities. Starting from GISS, there was always a mission support contract in place to provide support for civil service scientist research. The contracts are typically 3 to 5 years when they're rebid. I served on many source evaluation boards, performance evaluation boards, and I actually liked that. I don't know. I'm sorry? Well, whatever. I enjoy this kind of responsibility. There was a single contract supporting GMSB when it split into SDO and DAO, and the same contract, because a new one wasn't bid yet, supported both SDUO and DAO until after the split. And then separate RFPs came out. So I became the contracting officer technical representative, COTR, on the SDUO contract, later the SRT contract, and have been the COTR on other support contracts as well. This is one of my favorite stories. People know I tend to repeat things. Something happened in 2008. The Laboratory for Atmospheres, LAS, was having their holiday party. They have the annual holiday party. Jim Irons was the deputy director at the time, deputy lab chief. And I said, Jim, I can't come on that day. I was supposed to have some surgery. Well, the day before the party, the surgery was rescheduled. So I said, OK, Jim, I can come. But I hadn't bought a ticket. Don't worry, just come. At the party, Jim said I could do a little favor for him. Dick Stewart, the COTR of the LAS support contract, was retiring. Maybe, Joe, you could just be acting COTR on that contract for a while. We'll find somebody. And of course, the somebody became me. But only because I said I liked it, I'd do it. So then I became the COTR on two contracts. One was the LAS support contract, and one was the SRT support contract. And a new RFP came out in 2012 called Support for Atmospheric Sciences, SAS. That's the current contract that we have right now. And the SAS contract combined both the SRT contract and the LAS contract. Why? They were both coming due at the same time. You could have one less SEB and one less COTR, what have you. So I worked with Jim Irons to write the RFP for that. Somebody had to be the COTR, so I drew the short straw again, and it became me. And believe me, it's a big responsibility, but I enjoy it, and in particular, the challenging responsibility of interfacing between procurement and government scientists. I thought Karen would appreciate that comment. Okay, now let's get to AIRS, and the real fun begins here. AIRS, the Green Tree Sounder, was launched on EOS Aqua in 2002, and the main goals of AIRS were improving numerical weather prediction and monitoring climate processes. It's a passive, high spectral resolution IR spectrometer with spectral characteristics that were consistent with the pioneering work of Kaplan and Shaheen. I was involved in the design as well. And Mushaheen was the air science team leader, and I was an original air science team member. I wrote the theory, the basic theory of how we analyze that data. It's given in a paper over here. It's not important. This was a pre-launch algorithm. And it was fundamentally different from anything that anybody had done before. And there's a reason for this. It's both good and bad. It's fundamentally different because I never read anything that anyone had done, so I always come up with a fresh approach to how to do things. I did that in quantum mechanics too. It was always totally different. This was a pre-launch paper. We've had versions 4 to 6 of the AIRS science team retrieval algorithm. They all basically follow what I did with incremental improvements. Each time a little better, you learn, you make it a little better. And different geophysical parameters are solved for sequentially using observations in different channels. This is another story that I really liked. In June 2011, Piers Sellers returned to Goddard as the Deputy Director of the Sciences and Exploration Directorate after an illustrious career as an astronaut. He's a wonderful guy. And I saw Piers coming into the building, and I said, Piers, it's great to have you back at Goddard. Goddard needs somebody like you with a great sense of humor. And this is no joke. Piers said, Joel, that's you. I was really honored, but I'm nothing like Piers. His sense of humor is much better than mine, and he's provided outstanding scientific leadership here at Goddard, which has been made even more effective, I believe, by his marvelous and self-deprecating sense of humor. Now, so you know, he's been dealing with some health issues. He seems to be doing well, and we all wish him the best. Now, I want to say something about a typical AIRS science team meeting. We have AIRS science team meetings every 6 months, and a new version of the AIRS science team algorithm, which we use to reprocess all the old data and all new data, typically comes out 3 to 4 years. In a typical science team meeting, many scientists come up, including myself, having done research with the data that we produced, talking about how great AIRS version N data is. It's so much better than anything we've ever seen. And I get up there and say, yes, but N+1 is going to be much better. And this is all the time. The AIRS version 6 is what's currently operational, and the version 6 data set covers September 2002 through January. We probably have February by now, but we haven't looked for it. No, February's not done yet, through January. And version 7, God willing, is due for release in the near future. We hope maybe in 6 months or something like that. Here's a picture of the original AIRS science team. And there are a number of members here. I don't know if you can see it. Here, it's working. Here's Mushaheen. Here's me. There's a couple of people. Oh, Larrabee Stroh, if anybody knows Larrabee, he's changed a little bit, but he was there. We have a number of members from NOAA, Dave Walk, Bill Smith, Hank Revacombe, Larry McMillan, Mitch Goldberg. They were all on the original team. Alain Chadan was from France. He has George Oman from JPL. This was Roberto Calheiros. He was from Brazil. They built a special humidity microwave sounder that failed after 3 months. But one of the most important people on this team, who really never did much science, but was Catherine Gautier. She was fantastic because she was a professor at the University of California in Santa Barbara, and she hosted many an AIRS science team meeting over there, and it's just like heaven being over there. Okay, now I'm going to talk about some of the science that we've been doing. Oh, before that, this. As I said, the AIRS was designed primarily to measure temperature and water vapor profiles. But the science team retrieval algorithm, we said, we determined many things. And we determined a lot of other parameters, atmospheric profiles of ozone, other trace gases, cloud properties, outgoing long-wave radiation. And this enhanced capability has caused some tension between the AIRS science team and some other science teams, in the sense that there are instruments that are designed just to measure ozone, just to measure OLR, just to measure this, just to measure that, and we're putting out a competing product. and sometimes they looked at us and, with distrust at best. But in fact, I feel very strongly that being able to measure something from two different instruments, from two different ways, and if you get the same results, it's very strong. It supports the results of both instruments a lot. So, I'm going to show some results very soon about in two of the areas where we had some initial issues. One was outgoing long-wave radiation, for which Ceres was designed, and the other was total ozone, for which OMI and OMPS were designed. And I'm going to show examples of how well our products agree with theirs. And we're now getting along very well with these teams. I can see another one coming up. That's CO2. We're getting a good CO2 product. The OCO team doesn't want to hear anything about what we're doing, but I think one day we'll find that we're very complementary one to the other. OK, so now I'm going to show you some results. So the first three are climate-related. The last is data assimilation-related. Now, you've all heard, read it in the papers. Matter of fact, I read it about 2 weeks ago, so I told Lena, make this plot. So we read in the paper that 2015 is the warmest year on record. Well, our record only covers from 2003 through 2015. I'm just using whole years. And this is a plot of the global mean, annual mean surface skin temperature as a function of year, the difference of the surface skin temperature from the average of the 13 years. And if you take a look at it, these are the values, ups and downs. But there's definitely an upward trend here, and in particular, an upward trend over here. And here I have the slope of the least fit, straight line least squares fit to this time period, and there's a trend of 0.0123 Kelvin per year. Now this was from the surface skin temperature. Surface skin temperature is really very easy for us to measure from airs. The radiation is coming from the surface. We have these so-called window channels where there's very little absorption. You have to account for the little bit of absorption. And of course clouds, but we're very good at accounting for clouds. We do soundings in up to 90% cloud cover. So this was from skin temperature. And then there's another product that only recently I didn't think we could do, but we're getting very good results. We don't live on the skin. The skin is the ground, the ocean, whatever. We live in the air. So we also determine surface air temperature. And it's not a new product. It's a newly looked at product, a newly appreciated product. You'll see that we're getting very much the same result. The trend is almost the same. We're not really sensitive to radiation that's coming very near the surface, but the algorithm is very smart. It somehow knows what to do. And we get very accurate skin air temperature differences. So here, this is the global mean, but I'm showing you an annual mean temperature for 2015 minus the average of the annual mean temperatures of all of these years. And this is the spatial distribution of that. Reds and these greens here mean it's warmer. Blues and this color here means it's darker. It's colder. The darker the color, the bigger the effect. And yeah, this year is 0.19 Kelvin, global mean, warmer than the average. And there is global warming, if you want to think that way. But it's not global. People seem to think that everywhere, everything is happening the same. That's not the case at all. The warming that's been taking place primarily has been in the far north here. It's been taking place here. Greenland, for this particular year, and I'll show you something alluding to trends in a minute, has been cooling. I don't know why. I call myself an observationalist. I see it. You got to figure out why. But clearly, this has been cooling. Antarctica has been cooling. But it's very clear, this is what we're getting for skin temperature. It's being added. This happens to be an El Nino year, and you could see this effect of El Nino in the surface skin temperature. It's adding to this trend, but the trend was there before we had the El Nino. What's interesting is this plot for the surface air temperature, they're independent. So much so that if my answer here is too warm, my answer here is going to be too cold. They go in the opposite direction, and you could see that the spatial plots are very much the same. So this is one topic of interest. Now I'm going to switch gear and go to another. I mentioned outgoing long-wave radiation. Here, I'm using the word arcs. It's average rates of change. It's just short-term trend. Bill Lau had told me, you can't talk about trends for 13 years. So It's the slope of the least squares fit to the anomalies, and this is over the whole time period. And here's a spatial plot. Red means OLR is increasing over this time period. Blue means OLR is decreasing over this time period. And first, let's look at errors, and you'll see something. Now, OLR is the radiation going to space. If the surface is warmer, everything else being the same, there's more going to space. So typically at high latitudes, it's following what the land is doing. You'll see the effect that 2015, but the trend was warm over here, cold over here, cold over here. What's happening in the tropics primarily is the effect of El Nino activity on the distribution of clouds and water vapor. As you have more high clouds, radiation comes from the clouds, the OLR goes down. So here you're seeing some really big patterns of OLR that we compute from our products. Here's Ceres. This is a measured product. You'll see a very close relationship between what's being measured by an instrument that's just measuring flux, what we're determining from our products, what we're computing from that. This is the difference between them. The spatial correlation is 0.975. The agreement is really, really good. In the global mean sense, we have OLR decreasing by minus 0.01. They have minus 0.018. The difference is 0.08. It's insignificant. It's amazing that we get this type of agreement on a 1 degree spatial scale. What I'm not showing you is the absolute values also agree. These are just trends. We agree to better than 3 watts per meter squared, and Ceres wasn't designed to get results 3 watts per meter squared. So this is very important, but now I'm showing another. So this is a validation of both, and we can explain why these things are happening. And now I'm showing another use here, and this is the OLR coming from the MERA2 analysis from GMAO. It's the trend. They produce their own OLR. It's computed from their products. And if you look, you see that there's very good agreement. Their analysis is showing less coming from Greenland, more coming from here. These patterns are very much the same. But if you look at the patterns, it's interesting. So, you know, what they're doing is very good. And why are we doing this? We're interacting with the GMAO. Let's diagnose what's going on. Where do we think it's good? Where do we think it can use a little improvement? If you look what's going on here, you'll see this feature is much bigger than this feature. This feature is much bigger than this feature. This feature is much bigger than this feature. So while their model, their analysis is clearly responding to effects of El Nino and cloud distribution, somehow it's overdoing it. Also, they have this huge value of decreasing OLR over Africa, where we just have a hint of it here. So something is being exaggerated there. But it's really very, very good. And by the way, we looked at, I don't have time to show everything, we looked at the clouds. Their changes in clouds are very similar to ours, but somehow they got an increase in clouds here, which lowers the OLR. We didn't get that. And also, their global mean change is minus 0.1. We're minus 0.01. And that comes from the fact that for some reason their cloud cover has been increasing over this time period, including over Africa. And ours is not, and that's consistent with this measurement. Almost done here. How am I doing? Not bad. I'm going to go to the third science topic, and that's total ozone. Gordon LeBeau, who's here, who's been extremely helpful with us, he was tasked actually by headquarters to look to see if they can complement ozone results coming from the UV instruments, the state-of-the-art instruments, with other instruments like AIRS. We have some, ours is an IR instrument, theirs is a UV instrument. So we obviously have some potential additional information. For example, we can get it at night. They can't get it at night. So we can get it twice a day. And more important, polar winter. That's real. They have no idea what's going on in the polar winter, and we can get it in polar winter. But the important thing is they have to, before you can use them together, they have to agree. Gordon looked at our stuff for version 6. Joel, this looks real good, but what about this and what about that? And we made some improvements. We came up with a version called 622, which we ran at JPL for 2 months, August 2014 and 2015. And here we are showing the total ozone monthly mean for AIRS version 622 for August compared to OMPS. The agreement is actually very, very good. The spatial correlation is 0.96. You do see this feature over here, and we know what that feature is about. It's Saharan dust, silicates absorbing the ozone band. So if you see them, you can confuse it for ozone. We think we have too much ozone. We've been doing further research. We have something called 627, soon to be 7, where we don't improve on this, but we certainly know when it's happening, and we flag them as bad. We just gave you, did we give you a month? We're soon giving you a year of 627, and it's going to look a lot better, and version 7 is going to be better yet. But even so, this is, you don't just want to look at 1 month. I mean, you want to study the whole time period. A big thing you'll notice is there's not much down there. You can't, and we're getting very reasonable, good results here. And this is the interannual difference. Big features are happening from between 1 year and the other. We have an excellent agreement, a correlation of 0.96. So we're really excited about this one. Okay, last science result, and then I'll finish up. And I mentioned that we were doing results also on data assimilation that goes way back to when Bob Atlas was here, and we've picked up on that work. Bob Rosenberg works with me, Oreste Reale, and Erica McGrath from GMAO have been helping us a lot on this. And we're using a GEOS 5 data assimilation system, but we're looking at ways of possibly improving the way AIRS data is handled in the analysis. So I'm showing a result. This is the average of forecast skill for 52 forecasts run every day from September 10th through October 31st. And this is the 500 millibar height anomaly correlation. It's judged against the NCEP analysis. A perfect correlation means, a perfect anomaly correlation means the anomalies over the whole time period agree perfectly. The bigger the forecast, you begin to, you don't agree as well. A forecast skill of 0.6 is considered to be useless. And here I'm just showing you the results of what we got using the GMAO data handling methodology. And it's very good. The 7-day forecast has pretty good global skill. The research that we've done looking at different ways of handling AIRS and other satellite data has actually improved this. We're continuing to do more research on this. We're looking toward further improvements. And of course, one time period doesn't tell you anything. We're going to be testing it over different time periods, over different years. But we think the potential is good here. Hopefully, we can interact positively with them. OK, and now I'm going to, my next to last view graph. It would be my last, but the last is another hint on the price problem. So I call this my retirement plans. In January 2014, many people give these talks before they retire. Bill Lau gave a talk then, and he had no intention of retiring whatsoever, but Bill told me, headquarters understands you're retiring. He said, I'm not retiring. I have no plans on retiring. University of Maryland said, we hear you're retiring. I have no plans. Well, let me make you an offer. So they made him an offer he couldn't refuse, so he retired at that point. I have no plans on retiring in the foreseeable future. And there's a couple of reasons here. The main thing is, here's my wonderful group at SRT. Here's myself, Bob Rosenberg, Joyce Tompkins, Lena Iredell, John Blaisdell, Lou Kouvaris, and Jay Lee, who's not formally in our organization, but incredibly important part. And as long as I can continue to support these people, I'm gonna keep working. And there are a couple of reasons. The first is I still love doing what I'm doing. I think we're doing very exciting research. Like Lena, my guys say, we're never bored. So I'm really looking forward to AIRS version 7. We hope to get it out soon. It'll be applied to both AIRS and CRIS, which is another instrument that's flying on NPP now, and it's on NOAA satellites, different but similar to AIRS. And I'm also working with others toward the design of further advanced high spatial and spectral resolution sounders to determine not just improved soundings, but also winds, and we're really excited about the future there. Second is I actually enjoy being the COR. If I were not in the government, I couldn't do it. Karen's cracking up here. And I especially like working with Karen. We have a lot of fun together. She wouldn't let me retire. And as I said, I couldn't leave my group. We're like family. We just love it. So as long as I can keep getting money, let's keep doing it. There's a fourth reason I didn't put here. My wife, Leslie, works out of the house. She says, Joel, no way I'm having you home all day. So I plan to be here, hopefully, let's say God and NASA headquarters willing, I'll get some more money and be here for another couple of years. Okay, this is the last view graph. I hope I didn't go too far. This is another hint toward that prize problem. This is what I showed you before. We had a piece of paper. We had two lines. Construct the angle bisector of this. Someone said, why don't you just extend the lines? You can't do any work that's not on the paper. We're a big triangle. So I said, look, I gave you a hint. The hint said all the angle bisectors of a triangle meet at a point. Well, it sort of tells you what to do. I don't have any angles here. So you make an angle. What you do is you draw a line, make angles. And there you have it. And now construct the angle bisectors and now figure out what to do, which should be easy. And easier anyway. And I'll just say that if we have some time, I'll take questions. But what to do next is not one of those questions.